We'll go ahead and get started. So last week we were looking at additional systems, and I left off with synchrophasing, which was a more advanced version of synchronizing the propellers, where we synchronize RPM as well as the position of them. And what's the goal of synchrophasing? What's that? Eliminating vibration. What are the advantages of eliminating vibration or reducing vibration? Helps keep the propellers on. If they get extreme, they can leave the airplane. They run away. We had a plane hit a deer that broke off part of a blade, and it actually ripped the whole engine out of the nacelle. But fortunately, they didn't take off and have that happen. What else? What else is, so it reduces vibration. Reducing vibration does what for us? Why is that yeah. Yeah, so it helps with wear and tear on the aircraft, on the engine, right? What else? Reduces noise. That's the second one. There's kind of a third big element. What about all the people that are inside that tube? Makes it more comfortable. Okay, it makes it more comfortable for the individual. What about them? The heck with the passengers. What do we need them for? Just fly empty tubes around, right? No, it makes it more comfortable for the passengers and for the crew and for those operating. Okay, I'm going to go back through the slides. Just so before that, we talked about synchronizing, where we just do the RPM, and then I went through some of the other items. So review, auto feathering valve. How does the auto feathering valve work? What does it do? How do we auto feather the propeller? Simple term. What does the auto feathering valve do? Yeah. Returns oil to summit. It basically dumps the pressure. And these oil is used to move the prop to low pitch. Counterweights and centrifugal force move it to high pitch, sometimes spring. Okay. So to auto feather, we dump that oil pressure from the dome. So there's that. Unfeathering pump. What's an unfeathering pump used for? And why do we need it? So we can't adjust feathering. When can we adjust it? Yeah. Or when is it used? Okay, so we don't want to overstream the engine at startup. Are we doing it at startup or maybe just a little bit before startup? We would do it before starting the engine. It's essentially a source of oil pressure. It's an electric pump we can turn on in order to bring the blades out of feather. Okay, so, and then we talked about the overspeed governor. What's the overspeed governor do? What's the purpose of an overspeed governor? Is it a primary propeller control? No, what is it? What is it? It's a backup. It kicks in if for some reason the prop speed gets too high. Okay. What does it do? How does it fix that overspeed that's occurring? Ports oil pressure back to some. Again, we relieve oil pressure. Does it dump all the oil pressure like the feathering valve does? No, it dumps just enough to bring the blades to a coarse enough pitch that it slows the blades down until they reach the max RPM. Okay, so those were the systems we talked about already. And then getting into the last couple things that I want to talk about. So low pitch stops. On non-reversing propellers, on non-reversing propellers and reversible propellers, we absolutely never want the blades to go into that reverse position when we're in flight. Okay, that'd be really bad. Yeah, I see the pilots in the room are making funny faces. What would happen if we reversed our thrust on one side in flight? You'd throw the plane into a nasty spin. So any kind of thrust reversing device, in this case a reversible propeller, in some of the other classes we'll talk about thrust reversers on turbofan type engines, but in a reversing propeller you absolutely have to make sure it does not go into that reverse position in flight, because it will instantly go from producing no thrust to reverse thrust, and that's a bad, right? That's bad, okay? really bad. Yeah. So primary low pitch stops, they are a hard stop. They're typically a metal on metal contact point. When that blade hits that stop, it cannot travel any further. And it is usually part of the casting and machine surfaces that make up the hub and the blade, where when it reaches that low pitch position, they lock together, because reversing is going beyond the low pitch. It's going beyond a zero pitch position. Okay. Essentially the face and the back of the blade swap. You know, the face becomes the back becomes the face when you reverse that. So it sets the lowest possible blade angle, and it's almost always a hard stop. But when we have a reversing propeller, we want to be able to reverse it on the ground, but we absolutely don't want to reverse it in the air. And so if we had a permanent stop like that, a chunk of metal that was in there, we wouldn't be able to do that. So we got a couple different options for that. Let's dim the lights here. That'll help a little bit. So in many propellers, they are hydraulic, where if there is there is a mechanical linkage that's hooked to the oil control system, where if there's oil pressure, it's going to prevent it from furthering reversing in flight. Essentially, it creates a hydraulic lock. And that hydraulic lock pushes or sets a travel control into a position that does not allow the prop to go into reverse. It limits the travel of typically the piston, you know, that blade angle control piston, the servo piston, inside the airplane with a hydraulic lock. So how do you think that works? What does that usually tie to? It maintains oil pressure that cannot be, it maintains basically a bubble of oil, of non-compressible fluid, but we have to be able to get it out of the way when we want to reverse the propeller. So what do you think essentially opens a valve to allow that fluid to drain out of there in order to remove that hydraulic lock when we do want to use reverse? Where does that signal come from? A weight on wheel switch, okay? And oftentimes it is more than one weight on wheel switch. You almost always have a weight on wheel switch on at least your two mains. Some aircraft also have it on the nose, but more complex aircraft are going to have it on the nose as well. But it will require that oftentimes that both mains are on the ground, show being on the ground, before that hydraulic lock is removed. Essentially, it kind of works like an auto feathering valve, where it holds a certain amount of oil in behind the piston in the dome. And then when the weight on wheels switches engage, when the plane senses it's on the ground, it pops that solenoid open and allows that oil pressure, that oil to drain out of that stop area. Okay. Another way it can be done is with mechanical, and they're called secondary low pitch stops. And in this case, we have, they are a mechanical, they're almost like a pin that can go in and out. So it does the same type of a job, but these ones they're not removed until the plane is on the ground, until the plane hits the ground. And at that point, then they are retracted out of the way to allow it to move. And some will have both. Primarily, they rely on hydraulic, but then if the hydraulics fail, if they lose that hydraulic pressure, those pins are in place as well until the weight on wheels sensors indicate that the plane is back on the ground. And only then can the blades be physically driven to the reversing position. Okay. So you'll often, they're going to have some kind of a primary stop, and then they'll often add a secondary stop to be very sure. This is because it is so critical that they don't go reverse on, while the plane's in the air. Okay. Another system we'll have is called a negative torque sensing system. And on aircraft, if essentially, if the airflow through the propeller, if it's too easy for air to go through the propeller, and what this can be is a sudden dive, right? A sudden decrease in pitch of the aircraft and increase in speed, or gusts of wind, um, or things like temporary power, fuel disruptions, and high bleed air extraction at low power, things like that, can cause the torque on the propeller to go down where, remember, we're using an engine to drive the propeller. The engine is expecting there's a certain amount of load we have to put on that turbine engine or on that engine or a piston engine. And if the propeller all of a sudden can spin really easily because there's a bunch of air coming at it because the plane sped up into a dive, or when we have the reason this bleed air one, high volume bleed air extraction, that means we're pulling air off the compressor. There's less air to compress, so that compressor's going to be spinning faster. It can cause an overspeed of the aircraft, or of the engine. The engine can overspeed. And so it can cause an actual very low or even negative torque situation, where now the propeller, rather than the engine driving the propeller starts to drive the engine, which can lead to an extreme overspeed of the engine. And so we don't want that to happen. So these systems, if they sense negative torque, essentially the torque drops to zero or goes negative, will automatically drive the prop control system to put the blades to a higher blade angle, which puts more load on the prop, increases the amount of power that's needed to drive the propeller, and that increases the torque between the propeller and the engine. Okay, the more power you need to drive the prop, the more torque you're going to have, right? Torque is that twisting force. The engine's trying to twist the shaft. The propeller basically is trying to resist that. So by going to a higher blade angle, it makes it harder for us to twist the propeller in the air. And so it helps prevent these negative torque situations, and it helps to prevent the engine from ultimately overspeeding because of it. These are automatic systems. You can imagine there's probably nothing that the pilots are going to see to activate something like this. It's built into the engine. It would be another component kind of in this setup that would essentially port additional pressure, port full engine pressure directly to the propeller without it running through the prop governor. It would take the high pressure oil coming off the prop governor and port it directly to that without going through the pilot valve inside the propeller governor, the main governor. Okay. The last thing that a lot of these aircraft will have, more complex, and like the King Air has half of this, for instance, is something called an autocorson and APR. When I say some have half, there are aircraft that only have the APR portion of this. And APR stands for automatic power reserve. Okay? So an automatic power reserve is the system that in the event of a engine failure at a high power condition, where the engines are already at high power, and that's takeoff, climb out, the operating engine, so we lose power on a single engine, the operator engine will automatically be commanded to increase its thrust output. And it does that, it can do that two ways. The first is APR, automatic power reserve. The engine itself is forced to increase its speed to where it can sometimes go above the 100% operating range, upwards of sometimes 107% or more. On an aircraft with autocorson, what kicks in that APR, a turboprop aircraft with autocorson, is that the blade goes to a more coarse angle. It goes to a higher angle automatically. And the engine, the prop governor and engine are going to try that working engine. They're going to try to maintain the set RPM on the blade, on the propeller that it already is at, even though the blade's being driven to a higher angle of attack, higher blade angle. And so that's going to make the engine work harder as well. That's going to kick in that automatic power reserve, that reserve power that the engine has. And it can drive it, like I've got there, it can drive it sometimes upwards of 104, 105, 106, 107%. And it doesn't seem like a lot, but as you get near the top end of a turbine engine's power curve, power scale, small increases in percentage in RPM and torque result in larger increases in power available, essentially thrust available. And so we'll test these. This is something that we often will test by taking an airplane up to full power or near full power, and then essentially cutting back a throttle, and you'll see these systems can kick in place. And there's limits to how long they can run that way. Obviously, running an engine at 107% is not ideal. That's going to put a lot of wear and tear and stress on it. And so you basically often test that it activates and then immediately bring it back out of that range. Other turbine engines will do this as well, but they don't have the coarsening of because of the propeller, right? That's a thing. And so this is yet another system that, again, it's not activated by the crew. There is no way to automatically activate this unless you put it into like a test mode. You know, you as someone maintaining an aircraft, you often will have to test these systems. But unless you put it into a test mode, a pilot, a flight crew, often will never see this system operate. They may do a pre-flight test in some cases. They might, depending on their op spec and how the aircraft manufacturer says it should be tested, how often it should be tested, they may do some kind of a test related to it ahead of time. But it's very rare they actually activate the system wholly. A lot of these systems have a built-in test. They've got a test switch, you do the test. You really don't see much happening other than like a light comes on or a message comes on saying system test passed, or the green light comes on saying it's all good. And that's checking the circuitry and everything, the sensors. Like I said, it's a built-in test. In that case, it doesn't actually activate. You don't see an increase in torque, an increase in RPM, anything like that. But there will be times as a maintenance technician, you may actually do the actual activation test. And they're fun to do. Just know that what do you think the plane's going to want to do when you do one of these? Not going to want to go forward. It's going to want to spin in a circle. So we would do these in winter sometimes, and we would do it, and all of a sudden the plane would, we'd hit ice, and the plane would want to do a little pirouette at the end of the runway. Yeah, we wouldn't run them too often. Okay, so that's kind of most of the systems. And now, then later on, we'll talk about some of these more complex propellers more. We'll look at various, what are called operating ranges on them, how they operate, and then we'll do some tours and kind of go look at some of the physical propellers and that kind of thing in the coming weeks. So with that,